All right, so this is Jared Niemi with an in-class lecture about statistical modeling from the perspective of the two-sample problem. All right, so what we're going to be talking about today is the first question after you've read these chapters 2 through 4 in Statistical Sleuth is, all right, so I've learned all these different possible tests. Which one should I actually use? So that's the first thing we're going to cover. Then we're going to talk about p-values and their links to hypothesis testing. And these really just answer the question of, is there a difference on average between these two groups? Then we're going to talk about confidence intervals, which get a bit more information about how big is that difference, in which direction is that difference, and these kinds of things. And then finally, I want to mention that even these two, the test and the confidence intervals, don't really answer all the questions that we might have as a scientist. And what we might want to do is think about the problem from a prediction perspective. That is, if you got more samples, what would those samples show? Right? But in order to do this prediction piece, so we can kind of do the first two, the p-values and the confidence intervals, without making too many assumptions. But in order to do prediction, we really need to do some kind of statistical modeling. So that's going to be the main topic of today's lecture. All right, so the idea here is that you start making some assumptions about your data, and when you make these assumptions, you can say much more about what's going to happen than if you didn't make those assumptions. But then the caveat here is you need to go back and actually check that those assumptions are valid. All right, so that's what we're going to be talking about in today's lecture. From the text, this bottom part is particularly what Chapter 3 is about. All right. Okay, so that's the general outline. So the first thing is which test to use. Before we get there, I'm going to use this as a running example today. Here's some data about the carbon dioxide uptake of plants from Quebec and Mississippi. And we had an experiment where the CO2 uptake was measured at several levels of this ambient CO2 concentration. And about half the plants for each type, the types being Quebec and Mississippi, were either chilled overnight or not chilled overnight before the experiment. So for the purpose of today's lecture, until the very end, we're going to ignore sort of this whole part and just pretend we have a two-sample problem where we have plants from Quebec and Mississippi, and we're looking at their CO2 uptake. We want to say something statistical about their CO2 uptake and how they differ between Quebec and Mississippi. That make sense? By the way, you should feel free to ask questions whenever. All right, so we have a two-sample problem, right? We have some plants from Quebec, some plants from Mississippi. We want to say something about the difference in CO2 uptake between these two groups. Okay, all right, so that's what I was just saying. For now, we are only interested in Quebec versus Mississippi. And so here's going to be the way that we set up our scientific hypotheses. The null hypothesis is that there's no difference, and the alternative is that there is a difference. Right, so this is no difference in mean CO2 uptake, and the alternative is saying that there is a difference in mean CO2 uptake. This is between Quebec and Mississippi plants. Does it seem like a two-sample problem? Does it not seem like a two-sample problem? Right? Well, okay, it's not if you start looking at all the rest of this stuff, but if you just ignore that and say you have Quebec and Mississippi. Okay, so then the question is, all right, we've talked about lots of different tests for looking at this hypothesis, and so the question is, which test should we use? All right, so here's a diagram that tries to get at which test should I use. And this is a diagram that we'll come back to. It's a diagram that I thought I liked, and then I re-looked at it this morning and thought I would have now done it differently from the last time when I created it. So I probably will actually modify it after class and then splice into the video my new diagram and my new discussion about it. But this one still works. Okay. So here's the first idea. The question, you start up here and you say, how many groups do I have? All right, how many groups do we have? 2. This is a great projector, huh? So everybody agree that we have 2 groups? Quebec, Mississippi. All right. So for now, we're going to ignore this whole portion of this diagram, because this is what chapter 5 and 6 are about, is if you have more than two groups. And we haven't gotten there yet. Okay? So right now we're on two groups. All right? So I come here and I say, all right, are those two groups from a normal population? Right? So what are the things that describe a normal population? Or what are things that describe a population that's not normal? Skew? Outliers? Yep, those are basically it, right? This is what was talked about in chapter 3, but we're going to talk about it more today. So either, it looks normal or it doesn't look normal. And maybe you can transform it to normality. Right? This is like, if it's right skewed, you might take logs, and it might look approximately normal then. All right, so then you come back here. And then the question is, are the data paired or are they not paired? So are these data in this example paired or not paired? Right, not paired. Right, it'd be pretty hard for us to make measurements on the same plant, two different measurements on the same plant when the plants are supposed to come from Quebec, Mississippi. Right? So there's no way to pair this data. So the data are not paired. So then the question is, okay, do you have equal variance in the two groups or not? So do we have equal variance? Well, at this point, there's no way you can tell, right? I haven't shown you any data, right? But this is what you would want to check. So if they are equal variance, you do a two-sample t-test. If they're not, you do Welch's. If they're paired and normal, you can do the paired t-test. If they're paired and not normal, you can do the sign rank or the rank sum test, right? Depending on whether it's paired or not. Yes? Right, so variance, so we'll see some pictures later, but variance describes the spread in the distribution of the observations. Right, so if they have the same spread, they would have the same variance. So the book, I guess, that's a good point. The book often mentions equal standard deviations, right? And the variance is just the standard deviation squared. So there's just a one-to-one relationship between standard deviation and variance. Yeah. All right, so the thing I'm going to change about this diagram is I think that it makes more sense to put paired first. Right, and say, are the data paired or not? And then to look at whether they're normal or can be transformed to normal. All right, so that's the change that I'll make. Does it make some sense, though, how you would work your way through to figure out which test that you would want to use? Yeah. Okay. So, right. So at this point, we know that we have data that's not paired. And we don't know much about whether it's normal or whether it would have equal variance or it could be transformed to normal. Okay, so here's just running the test, right, without worrying too much about those assumptions because we're going to worry in a bit about those assumptions. This happens to be the R code to do it. Here we did both a t-test and the Wilcox and rank sum test. In R, the default is that the variances are not equal. So that is, it uses the Welch's t-test. So if you want to force it to use the two-sample t-test, you have to tell it that the variance is equal. And the main thing I want to get out of here is the p-values, right? The p-value here and the p-value here. Right, so this is the one that assumes normality, and this is the one that does not assume normality. The test that does not assume normality. Okay? And in both of them, we have a p-value that's really tiny, right? So what does that mean about our null hypothesis? Right, there's evidence against it. That's a good way to put it. Right? So that's fine. So we did these tests, and the question is, well, how much have we really learned about the data that we have, about this difference between Quebec and Mississippi? And so in order to know that, I want to just remind you what this p-value, the definition is. Right? I've mentioned before, but I'm a big fan of asking for the definition on an exam. Like, write down the definition of a p-value. So here it is. It's the probability of observing a test statistic as or more extreme than that observed if the null hypothesis is true. All right, so on this last slide, we had two different test statistics. Right? This is the one that comes from assuming a two-sample t-test, assuming the data are normal, and there's a different one for this rank sum test. So we had a decision there about which test statistic we wanted to use, but in both cases, it said that the data are highly unlikely, right? The test statistics are highly unlikely if the null hypothesis is in fact true. Right? So being a small p-value provides evidence against the null hypothesis. Right? What did I? Okay. But what have we really learned? Literally, we have learned that if the null hypothesis is true, then the test statistic is highly unlikely. That's really what we've said so far. Now, typically, what we say is that here's our nominal cutoff. Most people use a 0.05 cutoff. And if the p-value is less than that cutoff, what they say is we reject the null hypothesis. Right, that doesn't necessarily mean that your alternative is true. Right, it either means that your alternative is true or your model is really bad. Okay, and so we're going to talk a bit about checking the model in a bit. But at this point, what we can say is, okay, we don't believe that there's no difference between Quebec and Mississippi. All right, so does that seem very informative? Right, so you're the scientist, you went out and did this CO2 experiment, and you want to say something about differences between Quebec and Mississippi, and you come to me, I do the analysis, and I tell you, yeah, we don't think there's no difference. So, right, why is it not very useful? What might you want instead? Yeah, how much of a difference? And maybe which direction it is? Right? At this point, we don't even know if Quebec is bigger or Mississippi is bigger. Right? And we don't know how big that difference is. Okay, so the point here is that doing this hypothesis testing, getting these p-values, is not really very informative. Right? What you actually learn is very limited. So this historically is the way that most scientific papers were written. They just present the p-value. The literature is moving from just presenting p-values to presenting confidence intervals in addition. Right? Because confidence intervals end up being much more informative about what's going on. Right, so as you already pointed out, we might want to know which plant type has a larger mean CO2 uptake or how big that difference is. Those are the questions that are probably more interesting to you as a scientist. And in order to do that, we need to have a confidence interval. So now I just want to remind you of what this definition for a confidence interval is. All right, so this is often the way that we write it. So this alpha typically corresponds to that 0.05 that we had on the previous slide. So the common choice for alpha here is 0.05, which means that the common confidence intervals that you create are 95% confidence intervals. And the definition here is that this confidence interval, which we write in this fashion, right? We have some lower endpoint and some upper endpoint. So there's a confidence interval here for the mean difference in CO2 uptake between these two plants. This interval contains the true parameter, right? We think there's some true difference out there between these plants in their CO2 uptake. And that confidence interval is going to cover it, let's say 95% of the time, right? If it's a 95% interval. So what does that really mean? That means that if everybody in this room went out and did their own experiment, and you all created a confidence interval that's 95%, that 95% of your intervals on average would actually cover the truth. Right? So the intuition here is basically that it seems pretty likely that the true value is between this confidence interval that you created, right? Between the two endpoints of that confidence interval. So this now gives you some range for what seem like the plausible values for the parameter that you're interested in. In this case, the mean difference in carbon dioxide uptake. Does that make sense? No? Should we do the example? All right. So we do the example. So I don't know if you noticed, but nothing has changed up here. This t-test automatically gave you a confidence interval. So here the confidence interval is 8.8 to 16.5. It's not immediately obvious just from this which way we did the subtraction, right? Whether it was Quebec minus Mississippi or Mississippi minus Quebec. But you can tell right here, here are the estimates for the two groups. So Quebec has the larger estimate. So this confidence interval is sort of in favor of Quebec. Right? So what this says is that, right, we're 95% confident that the true difference of Quebec minus Mississippi is between 8.8 and 16.5. Okay? And again, this is now we've assumed normality. We're going to talk more about that in a second. This down here, we've not assumed normality. And if you go back a couple of slides, you'll see that the Wilcox.test, this function did not automatically create a confidence interval. You had to change an argument here to have it create the confidence interval for you. Right? And the reason for that is that it's computationally more intensive to create this confidence interval. And so by default, it's not going to do that extra computation unless you tell it, I really do want that interval. All right? So if you want that interval, here it is. So without any normality assumption, this confidence interval is 9.4 to 18.3, again in favor of Quebec. All right, so this seems more informative, right? Yep. Well, because I looked up here. Yeah, the same. Yep. Okay, so right, we had the normal assumption gave us one range. Without the normal assumption gave us a different range. But we at least know that the difference, the mean difference in CO2 uptake between these two populations is somewhere in this range. That seem helpful? Does it seem at least more helpful than just the p-value, which tells you there's no difference? Okay. So how might you get this confidence interval to be narrower? Oh, you could change alpha. Is that what you're saying? Yeah, you could certainly change alpha. So I guess my question should have been, if I want to keep a 95% confidence interval, so I want to keep alpha, how might I shrink this interval? So increase the sample size. Yep. Okay. So this seems helpful. The only caveat here is that, okay, right, these are the questions we've answered. Maybe I should have pointed that out. We've commented on which has larger mean uptake, right? We now know that it's Quebec. And we have some uncertainty about what the mean difference is, right? It's somewhere in the range 8 to 17, something like that. Right? But the key here is that we're still only talking about the mean difference. So what if we're interested in something about, here's two new plants, one from Quebec, one from Mississippi, say which one's going to have a larger CO2 uptake? Right? This isn't going to answer that, because this only says on average. So if you took all the Quebec plants and got their average, and you took all the Mississippi plants and got their average, right? The Quebec plants seem like they're going to be larger in CO2 uptake than the Mississippi plants. But if you want to make a statement about these two plants, let's say, we haven't answered that question whatsoever. Right? So this says which plant type will have larger CO2 uptake in the future. Right? This is a prediction. Is it clear that this is a prediction about what's going to happen? Okay. Right. So we need to make a prediction. In order to make a prediction now, we need a statistical model. All right, so now we're going to talk about modeling. And the reason we're going to talk about modeling is to say something about what's going to happen in the future. Questions at this point? It's going to sound odd on YouTube with the big pause, but guess I could cut it out. All right, so let's talk about modeling then. I want to introduce two new terms. The terms are nonparametric and parametric. I can't remember, does the book mention the term nonparametric? Not so far. Well, it won't later. If it did, it would be now. All right, so first I'm going to introduce nonparametric statistics. This is an approach to doing statistics where you do not assume that your data follow any particular distribution. Right? So the examples of these nonparametric statistics that we've talked about already are everything that was in Chapter 4. Everything? Was Welch's t-test in Chapter 4? Okay, everything other than Welch's t-test. Right? So the rank sum test, the signed test, the signed rank test, the Kruskal-Wallis test, which we'll talk about later, I think in Chapter 6 when we get to more than two groups. Right? So these things. The rank sum test, the signed test, the signed rank test. These were all non-parametric approaches to doing the hypothesis testing and getting a p-value and getting confidence intervals. So the opposite, parametric statistics, does assume that your data follows some known distribution. And this distribution has some parameters in it that are unknown. Okay, we'll talk about that in a second. So the key here is that parametric statistics, the data follow a particular distribution, say normal distribution. That's the one we're going to be using for almost the entirety of the class. And that normal distribution has some parameters, the mean and the variance, or the mean and the standard deviation. And those parameters are what are unknown. Right, so examples of this one are the two-sample t-test, the paired t-test, and Welch's t-test. So notice that all the ones that say t-test. And all of these are parametric approaches. All right. So I think I've got some math notation, and then I've got some pictures. Okay. So we're going to focus now on it. Right. So this is what we would call statistical modeling. We're actually modeling the data that we have by assuming, in this case, a normal distribution. Right up here, there's no real statistical modeling going on. And basically, with the only caveat being the Kruskal-Wallis test, for the rest of the semester in this course, we are going to be doing modeling, statistical modeling. So this non-parametric approaches is limited to just Chapter 4 and this Kruskal-Wallis test. Okay. So I'm going to introduce some statistical notation now. All right, so here we're going to let Yij be the actual observation, so in this case, the actual CO2 uptake for the jth observation, so in this case, the jth plant in the ith group. And so I here is either Quebec or Mississippi. So like Y11 would be the first plant from Quebec. Y22 would be the second plant from Mississippi. Right, and whatever its CO2 uptake was. Okay? So you fine with that notation? So typically whenever I'm solving a problem, so a client comes into me in the Statistical Consulting Center and they say, here's my data. The first thing I do is I write down notation like this. I say, let's let Y be whatever it is the response that's of interest. Right? And I make sure that I get the right subscripts here. In the two-sample test, this is all you need. Right? It's always just Yij, and Yij is equal to something. In this case, the CO2 uptake for plant J in group I. Okay? So then, here are the assumptions for the three parametric tests that I listed on the last slide. So the first one is the paired t-test. Well, if the data are paired, right, the first thing that we do is we take the difference within each pair between the two groups. So this is not the kind of data that we have here because the data are not paired. But you had, for example, the unaffected and affected populations, I think in one of the case studies, right? Yeah, does that sound familiar? Okay. And the first thing that you did in the paired t-test is take the difference for each pair. Right? So that's now a new notation, dj. So that's the difference for pair j. And the assumption here is that they are independent and normally distributed with mean mu and variance sigma squared, or alternatively standard deviation sigma. So then we go on to the two-sample t-test, and things look very similar. Right now we actually model the data, not the differences, because we don't have pairs. But the data are independent from a normal distribution with some mean that depends on the group. Right, so this means that there's a different mean for the Quebec population than there is for the Mississippi population, but with the same variance or the same standard deviation. So perform what twice?
I'm assuming that's the formula for a calculation and not later.
Yes. Well, this is the assumption that leads to the t-test and the confidence interval associated with it. So this is the assumption that leads to those formulas like y1 bar minus y2 bar plus or minus the t cutoff times the standard error of y bar 1 minus y bar 2. Right? So that equation for the confidence interval, right, comes because you've made this assumption. Is that what you're getting at? Well, no, it's not what it tells you. This is what assumptions you're making about your data. Yeah, so we're going to talk about that. We're going to talk about what these assumptions mean. Yep, and more importantly, when you can look at your data and see that those assumptions aren't true. Yep, so that's what we're going to talk about on the next few slides. But the main point of this slide is that in each of these cases, we're going to be making a normal assumption. Right, so the last one here is the Welch's t-test. And the difference between the two-sample t-test and the Welch's t-test is now that each group has a different variance or a different standard deviation. Right, so this sigma has a subscript I. But always the data are independent. They're always normally distributed. Yes? So yes, that's true. So this, okay, so let me point that out. That's a good point. So here, I want to point out that mu and sigma, right? So maybe the mu I and the sigma I, but the mu's and the sigmas here are called parameters. And it's standard by convention to put these parameters in Greek letters. Right? And all this means is that somewhere out there, you believe that there's a true mu and a true sigma for the entire population that's of interest. Right? So that gets to your point. You've taken your sample and you've calculated what the mean is and what the standard deviation is in both groups, but that's just the mean and the standard deviation of your sample. These are the mean and the standard deviation, let's say here, the mean and the standard deviation in the population. Now, to your other point, there's no reason that they have to be the same in the population. Right? And so that's mainly what we're doing when we're getting the hypothesis tests and confidence intervals. Right? In that case, we're saying whether the mu1 is equal to mu2. Right? In either this case or this case. Up here, we're saying mu is equal to 0 or not. Right? Are the differences 0? We probably won't talk about it much, but there are ways to test for the variances being equal as well. And in fact, in SAS, when you do proc t-test, the very bottom line says test for equality of variances. So right there, it does the test for whether the variances are equal. We're not going to talk about it so much because for the rest of the course, we're always going to be making this assumption. So when we get to ANOVA and regression, the assumption is always that the variances are equal. And we'll still go back and look at whether that assumption is reasonable or not. but that's the assumption that's going to be made basically for the rest of the semester. So this is really the only time that the variance is not being equal is an option. Yes?
For the three different tests, follow the normal distribution. But only for the two first cases, we don't have, for the two first cases, we have the same variance, but for the quantitative test, we have a different variance. For the three of them, follow a normal distribution.
Right. So in all three cases, it follows a normal distribution. In here, there is only one variance, right? Because there's only a set of differences. So here, that seems totally reasonable. Whether normality seems reasonable or not, that's a question. Here, right, there are sort of two variances because there's two groups. And so one of the questions you might ask is whether this is a better model than that. That is, you have allow separate variances in the two populations or have a common variance in the two populations. This ends up being often a very reasonable assumption. And the book points out that you only get into big trouble with the t-test if these variances are really quite different, right? Like it's twice as big as one's twice as big as the other, right? If one's 10% bigger than the other, you're probably fine still with this assumption. Okay, so let's get some pictures, right, for what these assumptions are doing. Yeah, so I wanted to point out just again that when we go forward in the course, so chapters 5 and 6 are about ANOVA, and then after that we start talking about regression. And these normality assumptions are going to be made for ANOVA and for regression. Okay, so let's look at some pictures. Oh yeah, okay, good. I'm glad that I put both the, these are supposed to be black and red, right? But at least I also made them a different line type so you can distinguish them. All right, so starting from the left side. The left side, the assumption here is that the differences come from a normal population. So all that means is that if you were able to make a histogram of all the observations, of all the differences, say in the whole population, it should look something like this, right? Like a bell-shaped curve. And then the question is going to be whether that distribution is centered at 0 or it's centered somewhere else, right? That you expect the differences to be 0 or not. So pictorially, this is the assumption you're making in the paired t-test, that the differences come from this bell-shaped curve. Questions about that? All right, so if we move over then to the t-test, the t-test says, okay, well now you have two different groups, right? And those two groups have possibly different means. Thus, one of the curves is shifted relative to the other curve, right? Here the solid line is left of the dashed line. And you've assumed in the two-sample t-test that the variances are equal. Thus, the width of these curves and the height of these curves are the same. So what that means is that what you believe in the population, if you were able to take a histogram, say, of all the Quebec plants and their CO2 uptake, what you would see is this black curve, solid black curve. And if you were to plot a histogram of all of the Mississippi plants, you would see this dashed red curve. Now, we've actually seen that Quebec has higher CO2 uptake, right, than Mississippi, so you might reverse that. But the assumption so far has been that the variability in the CO2 uptake in those two populations is the same. Right? Thus, these two curves just look like the same but shifted. And the question becomes, all right, is that shift 0 or is that shift not 0? So then, finally, we look at Welch's t-test. Welch's t-test says, all right, so we have two normal curves. So the populations still come from these bell-shaped curves. But those bell-shaped curves might look quite a bit different. Right? They're possibly shifted. So the peak of this curve is here, and the peak of this curve is here. And the width of the curves are different. Right? This comes because there's a different variance or a different standard deviation. And similarly, the height of the curves are different, again, because of the variance and the standard deviation. So one of the questions would be, if you did take a histogram of the whole population of these Quebec plants and Mississippi plants, does it look more like this picture or more like that picture? So are the variances in the populations the same, or are they different? Yep. So, well, no. So I wouldn't say that. So the comment was, whether if you got the same results from the two-sample t-test and Welch's t-test, could you then assume that variances are equal? So no, right? What you can assume is that, so your analysis is now robust to whether or not the variances are equal, right? Because those tests only look at whether the means are the same. Right? And in particular, in the text, it comments that if the sample sizes in your two, in the Quebec sample and in the Mississippi sample are the same, then being off, then having different variances isn't such a big deal, right? You're still going to get the same results with the two-sample t-test or with the Welch's t-test. Okay. All right, so pictorially, this is what these assumptions mean, right? If you were to plot the entire populations as a histogram, they would look like these curves. Okay, so I wanted to point out here now that getting a confidence interval, getting an estimate of the difference in those curves, the difference in the mean of those curves, isn't everything, right? And so here are two different examples where the actual true difference between the two curves, that is where the means are on the two curves, that difference is the same, right? So this curve is centered at -1, this is centered at 1. That's the difference, which is 2. Over here you have the same thing, right? This one's centered at -1, this one's centered at 1. So the difference there is 2, right? So if you were to construct a confidence interval from data from this population and data from this population, you could get two confidence intervals that are exactly the same. But yet, these populations look quite a bit different, don't they? In particular, these bell-shaped curves hardly overlap, right? What that tells you is that the vast majority of the individuals in this population are bigger than the individuals in this population, right? There's only a few of them that are smaller. In contrast, these two overlap quite a bit, right? So in the populations, there's not so much different between these two individuals. So this is where I wanted to say that confidence intervals aren't the end-all, and what you might want to say is a prediction. You might want to say something like, well, what's the probability that the CO2 uptake in a Quebec plant is going to be larger than the CO2 uptake in a Mississippi plant? If this is reality, that probability is going to be really large, right? Almost all the Quebec plants have higher CO2 uptake than the Mississippi plants. If the picture on the right is reality, well, that probability is not going to be so big. It's going to be greater than 50%, right? Maybe it's like 60%. So this is a comment about the variability in the populations relative to the difference in the means. All right, so that's why you might want to make predictions. Yes?
Doesn't the 95% confidence interval have something to do with the variance also, or is that not part of?
Yes, so in the construction of the confidence interval, you essentially plug in a point estimate for that variance, right? This pooled standard deviation piece. And so what's going to happen is that, in these examples, you would need a lot more data in this population, from this population, than you would from the population on the left in order to get the same confidence intervals. So that's how that's going to come to play. So my point is that if somebody just gave you the confidence intervals, they said, here's the confidence interval for the difference between these two populations, that's not sufficient information to tell you anything about making predictions about what's going to happen in the future for individual plants. Okay. All right, so, this just reviews. All right, so yeah, now I want to talk about, so we're interested possibly in making assumptions, creating a statistical model for our data, in order to make predictions about what's going to happen. And so one of the things we need to do is to look at our assumptions and be able to test whether those assumptions are valid or not. Right? So here's the assumptions for the two-sample t-test, and here's ways that things can be violated. Right? So this is ways that the normality assumption right here can be violated. We've already commented on them. If the population is skewed, if it's heavy-tailed, that is that there are outliers, if they have unequal standard deviations, right? We've assumed here that the standard deviations are equal, and so one way that we could violate that assumption is that we have unequal standard deviations. We can also violate this independence assumption by having data that are clustered somehow, data that have some kind of serial effect over time, data that have some spatial correlation. And I'm adding, so this is what the book basically talked about, and I'm going to add another one that we are missing some explanatory variables. All right? So we have ways of dealing with some of these within the context of the test that we want to do. This is supposed to be in red again. So if it's skewed, if the data are skewed, you can try taking logs, and maybe then the logs of the data look approximately normal. If the data have unequal standard deviations, we mentioned that if you have equal sample sizes, then you're going to be pretty robust to the fact that they have different standard deviations. Alternatively, we could use Welch's t-test. Right? So we basically have ways of dealing with a couple of these pieces. The statisticians have ways of dealing with all of them, right? But the rest of them we're not covering in this class. So you'd have to take another class to figure out, right? These basically are adding in random effects to your model, which we're not going to talk about. We are going to talk about this bottom one, right? If you're missing the explanatory variables, then the easiest thing to do is go get them, right? Or put them in the analysis. All right, so here's just a picture of what those first normality violations look like. So what I have here on the left are data that are skewed. In the middle, data that are normal. On the right side, data that are heavy-tailed. Right? And what I've done is I've just simulated some data. That's shown in the histogram. So each of these histograms is just simulated data. This one from a skewed distribution, this one from a normal, this one from a heavy-tailed. And I've plotted on top of it, this is the best-fitting normal curve. So if this population were actually normal, then it should follow approximately this curve. All right, so it seems pretty clear that the skewed data, right, we have a lot of observations that are on the left side of this curve, and only a few observations on the right side of this curve. Right, so if you see, right, SAS by default will print out histograms with overlaid normal curves. So if you see something like this, then your data are skewed. Here's an example from data that are actually normal. Right? Does that data look like it comes from that curve? Yeah? I'd say it doesn't really look like it, but right, this is, all of these were with 100 observations. So the point here is even with data that truly comes from a normal, right, you can get things that don't look that normal. Right? Here is a data that come from a heavy-tailed distribution. If you compare this heavy tail versus the normal, I mean, they don't look dramatically different, do they? And yet, this one is problematic, the one on the right is problematic, and the one in the middle is not. All right, so we have some better tools than just looking at histograms and overlaying a normal curve. So the best tool that we probably have is the QQ plot. All right, so for now, we're going to talk more about the QQ plot later, but for now, I just want to point out that on these QQ plots, if the points fall right on the line, then you're good. Right? Then there's no evidence that your data are not normal. The one on the left here, there's a clear tail in the bottom going way away from the line. Okay, that's evidence that there's not normality, in particular that we have skewness. And the one on the right, okay, these data look pretty good, right? And there's maybe a little bit of evidence down here that things are varying away from the line. Okay, again, we're going to talk more about QQ plots, but I just wanted to point out that we have some better tools than just looking at histograms with overlaid normal curves. All right, so I think now I'm going to look at the data set that we actually have. All right, so here's the Quebec population and the Mississippi population. Right, again, we have the histograms of the actual data. We have density normal curves overlaid. Right, these are the best fitting normal curves for this data and for this data. And then on the bottom we have the QQ plots. All right, relative to the last slide, do these QQ plots look good or look bad? Does everybody agree that they look bad? They look not, well, that's bad. Okay, good. I like it. Let's be more specific, right? Do they look normal or not look normal, right? They don't look normal. Yes? Yeah, sure. You could get, yes, you could get sort of limits here if you wanted to. Yeah. Okay, so why? Right? Why do these data look so not normal? Anybody have a guess? Small sample size, that's true, yeah. The other thing is that, right, we ignored a bunch of stuff here for the design of the experiment. We've ignored that we actually have a clustering effect, that half the plants of each type were chilled or not chilled. Right, so that's going to be a clustering or equivalently a missing explanatory variable. We've certainly ignored this other one, that we did this at several levels of ambient CO2 concentration. So here's an explanatory variable that we've completely ignored. So we're going to come back to this data set when we go to ANOVA and when we go to regression, right? Because then we're going to take into account these other factors that we're ignoring at this point. All right? All right, so just as a quick conclusion slide, we talked initially about p-values and found that this is the key thing to remember. A lot of people were getting this wrong on the IRAT, so I wanted to point it out. Small p-values provide evidence against the null hypothesis. But these are not very informative, right? All they tell you is that we don't think there's no difference, right? Confidence intervals are more informative, right? They provide the magnitude of the difference and its uncertainty. That's much more useful. And other people are getting this one wrong. So a 95% confidence interval covers the true value 95% of the time, right? That's the whole point of constructing that interval. But I showed a slide where vastly different populations can give rise to the exact same confidence interval. So even knowing the confidence interval isn't everything, right? You need to understand the variability that exists in the population. And so I mentioned that what we might want to do is predictions, right? So that can answer some questions of scientific interest, but we need a model to do it. And I basically left you hanging about what we're actually going to do there, right? Because we're going to come back to making predictions.